Sequences and series. So for the most part, we're going to be talking about series, but it's the title of the unit is sequences and series. A sequence is essentially a pattern, right? So we've got individual terms or elements of our sequence, and they follow some kind of pattern. They're separating them by commas. It's a sequence. It's a pattern. You've dealt with sequences all your life. A series, though, essentially is adding those values of a sequence as we go. You know, jump on me because it's easy to mix up the word sequence and series. So if I'm not clear, you know, just demand that I am. But notice how we've got the terms of a sequence as A1, A2, A3 separated by commas. The terms of a series are adding along the way. So we're finding that next term, we're adding it to what we previously had. A series is adding along the way. Essentially, to define a sequence, we typically refer to it with an A. A typically denotes a sequence, whereas S is talking about a series. So if A of n is the sequence, so we plug in a 1 to find the first term of the sequence, a 2 to find the second term in the sequence, a 10 to find the 10th term in the sequence. If we're adding them along the way as we go all the way to infinity, then we are adding all of the values of our series. We're adding them as we go, we're collecting them, our summation is adding them. So a series and that summation go together. We're finding that next term. Remember, we did a few of those. It's kind of like a little of an intro where we realized that when we're doing a summation, we're listing them out, but we're adding them along the way. Those were series. So that little n tells us the term in the sequence that we're looking for. So if we wanted to find the third term, it would be 10. If we plug in a 1, we get 6. If we plug in a 2, we get 8. If we plug in a 3, we get 10. A summation, well, we're adding along the way. So if I wanted to find S of 5, that means that I'm going to add the first 5 terms. I'm going to go all the way out to the 5th, and that's where I'm going to stop. And we call that a partial sum, because we're not adding all the way out to the infinite, like the infinite term. We're stopping at 5. So it's just a partial sum. So we can have a sequence that's just nice, consistent, 6, 8, 10, very predictable like this. We could also have a sequence that changes signs. Changing signs, positive, negative, positive, negative, positive. That's possible as well. Ultimately, everything you know about a sequence is still true, and a series would be adding them along the way. A partial sum would be stopping and only adding up that many of the values. Thoughts about any of this stuff? And while we see it, this term is not an important piece of vocabulary for us at the moment, but it will be a series where we are changing signs. each term is changing signs. We call that an alternating series because it's alternating between positive and negative numbers, and that will be important for us one day. All right. All right. So, does a sequence converge or diverge? And we kind of used those terms a little bit before in the past, converge or diverge. And notice we are talking about, specifically we're talking about a sequence right here. This whole slide is very specific to a sequence. A sequence converges if our limit as n approaches infinity. So as we look at that infinite term, the last term of our sequence, if this equals a constant value, then it has converged. It is converged at a nice constant value. But if our limit as our term approaches infinity of a of n doesn't exist, like if it goes to infinity, then it diverges. Converge means we've resolved at a nice finite number. As we continue to look at the next term and the next term and the next term, they're getting us somewhere if it converges. When we look at that last term in the sequence, we know it's going to be a constant value. But it diverges if it does something like approaches infinity. We would never get there. If we keep looking at that next term in the sequence, the next term in the sequence, the next term, it just keeps changing. Maybe it's going between positive and negative infinity. Maybe it's just bouncing between positive and negative 2. That would be a diverge as well. But if it's not approaching some nice constant value, it diverges. All right. Think about these. Okay, these are all sequences. Okay, take a look at this sequence. All right. I'd like you to think: would this sequence converge or diverge? Okay, you can have some conversation. You don't have to do it all by yourself. Let's think: does it converge or diverge? And then let's find each of these. What would be the fourth term in the sequence? What would be the partial sum of the first 4 terms? Notice what this would be asking us for. So think through these, whether we're given an expression or the beginning of a pattern.
First one, divergent.
The first one.
Go what?
Like an interval.
Oh yeah.
Like really long and stuff. Okay.
And so if it goes to like infinity or negative infinity, it's still diverges, right?
Yeah. Oh yeah.
Okay.
Because the limit doesn't exist.
It's -10, right? 7, 7, 2, 7, 7. Is diverging.
The odd number.
So it would be a 0.
0.
Mm-hmm. 2, 3, 5, 7, 11, 13. Those are all the prime numbers.
That's the sequence.
Yeah. It's diverging. And then, wait, what was the also?
What's kind of
8.
That's the date. There's a difference of 1 and 2 and 2.
And then 19. So.
How do you know it's 19?
It's prime numbers.
Oh, I thought they were like patterns,
That is a pattern.
like math patterns.
It's 77. Um,
Is it Diverge?
yeah,
I think
I
it's
think
Diverge.
it's diverging.
-1, -2.
So it would be, yeah, negative 1. Can we, well,
Mm-hmm. Listening?
I think, is this one diverging? But it would be like an indeterminate form.
Interesting, huh?
So can we use L'Hopital's rule?
Sure, if you want to try L'Hopital's rule, sure. Try it out.
I really don't
You
know if
get,
that works.
I mean, it does, because it's infinity over infinity.
Right.
So you're welcome to do a L'Hopital. For the sake of this, I mean, the L'Hopital rule would probably be good practice, but for the sake of this, you are also welcome to, you know, mess around with the calculator if you want.
I got 0. For which one?
I think it can, I think it converges. It's, I plugged in 100. Which one? For the last one. Plugged in 100. I got 0.
I think it's divergent since it was 2 ways.
Cause like if you plug in anything, it'll give you that number. Then on the bottom
I
it'll
don't
give you a
know
bigger
that
number.
graph.
It'll give you a bigger number.
It's gonna be 0. Yeah.
What's your graph? Is mine already full polar? No, mine looks different. Wait, why did you change to that one? No, I changed it. I just went back to that.
So what did y'all decide for that last one? What was the limit?
Converging 0.
Converges to 0.
Mhm.
Should we L'Hopital? Do we want to see how that
I
works?
didn't actually L'Hopital it, but we can, yeah.
Well, I mean, it's always good practice to
Yeah.
make sure. So if we didn't have a calculator, that would be a way that they could integrate L'Hopital's rule and what we know about limits
Mm-hmm.
into a question like this in the AP exam. Does this sequence converge or diverge? Because just looking at it, I have a prediction. I would predict it goes to 0, but that's because remember what we talked about when we talked about L'Hopital's rule. Like an exponential function grows exponentially, and a quadratic is just kind of doing its quadratic thing. So I would assume that this would go to infinity faster than this would go to infinity. The bottom wins, and so I'd expect it to essentially be infinity on the bottom. So that would be my expectation. So the problem with this is that when we go to take the derivative, the top is easy, the bottom we can get rid of that -1. But we have to take the derivative of this 2 to the nth power, and we probably all have forgotten the rule of taking the derivative of a constant to the power.
Yes.
Anybody remember that? So I'm just going to give myself a little bit of space up here. if I'm trying to take the derivative of that, I'm just going to call it y equals 2 to the nth power. What we did is we applied natural log to both sides. We were able to kick the n to the front. When I take the derivative of both sides, this gives me, or I can just write it like this, the derivative of y over y equals natural log of 2. And when I move the y back over here, I have the derivative is equal to, knowing that y is 2 to the nth power times natural log of 2.
Yep.
So notice that as the exponent decreased for a polynomial, 2 to the nth power like almost got more powerful. Like we went from 2 to the nth power to 2 to the nth power times something. We've gotten stronger as we've taken the derivative, which kind of makes sense because the slope is going to be greater. Okay, so this, and you can imagine what would happen as we take a derivative again. We would then just have 2 on the top, but we would still have 2 to the nth power on the bottom. 2 to the nth power wins out. Our limit as n approaches infinity of a of n is 0, and because 0 is constant, that means, how am I spelling? Converge. It converges. So I highly encourage you to use everything that we do know about limits in calculus, but also to kind of question it and to try to think about what's going on, because the more logic and practical, like common sense that you can apply to understand these kind of things, the more this whole unit will end up making sense. There's going to be situations where you're going to say, I'm just going to apply calculus. I'm going to let it answer the question for me. But there's also going to be times where what to apply, you do something, you're like, did that work? But then when you look at it and you say, okay, that makes sense, or okay, that doesn't. Because ultimately, like, the whole unit comes down to stuff kind of like this. And we have a lot of experience with patterns. You've used patterns for years and years and years and years. Okay, so please apply common sense, but ultimately we want to back it up with calculus. All right, cool. Okay, let's talk about partial sums. This is exciting. This is exciting stuff right here. It says the nth partial sum. So this is where we have to be careful with S versus A. A is talking about the term in our sequence. S is talking about the sum. S of n is saying that this expression right here is representing the sum of the first n number of terms in our sequence. Everybody see that distinction right there? That expression is not telling us the terms, as we just saw. If I plug in a 1, that tells me the sum of the first term. If I plug in a 10, it is the output of plugging in a 10 is the sum of the first 10. Okay, is that, we good with that? Notice what we want to find. We want to write a rule that represents A of n. So let's do some exploring, 'cause I want this to make sense right here, because this is one of those things that I don't have rolling around in my head. But as I think about it, I see what to do. So I can kind of put things together. Okay, let's make up a sequence. Okay, let's count by twos. Okay, 2, 4, 6, 8. All right. A of 4 is 8. What is S of 4?
20.
20. Yeah, right. Yeah. A of 4 is 8. S of 4 is 20. If I want to represent A of 4, if I wanted to find what A of 4 is, A of 4 is equal to S of 4 minus S of 3. Because if I add up the first 3, and then I add the very next, I get S of 4. Right? That is the definition of S of 4 is adding up all the ones before. S of 3 is already added up the first 3. We add the fourth one, we get S of 4. So, if I want to write a rule for A of n, then I can take, just to think of it in terms of this, S of n minus 1 plus A of n has to equal S of n. Add up all the terms before it, add that very next one, and we get the sum of all the terms we've looked at so far. To rearrange, A of n, which is what we're looking for, is going to be S of n minus S of n minus 1. See that, Keisha? And that's what we want to work out. That'll be our last problem of the day. Let's actually do this. So S of n minus 1 would literally be plugging in an n minus 1 everywhere we have an n. Subtracting away S of, oh sorry, I wrote that backwards. S of n minus S of n minus 1. Got excited about plugging in that n minus 1. At this point, we have represented the expression. We probably want to be able to simplify it. I would think that probably Khan Academy would simplify if you saw it there. If this was on a multiple choice exam, they probably would simplify it as well. So first thing I would do is I would clean up probably the numerator right there. N plus 2 over n minus n plus 1 over n minus 1. We've got to get common denominators, and then we can combine everything. So this one over here needs to multiply by n on the top and the bottom. This one over here needs to multiply by n plus 1. No, n minus 1. Minus 1. N minus 1 on the top and the bottom. So the denominator is the same now. But our numerator, n minus 1 times n plus 2, minus n times n plus 1. And at this point, it's just about cleaning it up to the point that we can match a multiple choice answer. And if we don't have to match multiple choice answer, this first thing would be fine. You know, do we want to see that worked out? Are we good with that? What do we? the big thing is this right here. After that, it's algebra. And really, we aren't really applying calculus here. We're just still understanding sequences and series.